Okay, what about now? Oh, good. Okay, so I would just go back to what I was just talking about. So that's how I define the reaction rate. Okay, so okay, so now I guess my iPad is working again. So that's how I define the reaction rate. And then for equilibrium, it means that the reactant side and then the product side forms some kind of balance. And what I mean by that is the forward reaction is equal to the reverse reaction rate. So a lot of times we think that once the reaction is completed, then no more reaction is occurring, but actually it's not. So from the macro perspective, we do not see any of the changes. When I say macro perspective, I mean the mass or the volume of the reactants and products are not changing anymore. But if you take a look at the particle level, actually there are reaction going on like for toward both sides. And how I usually explain it is, okay, so let's say I am based in LA. So let's say at the very beginning, LA has a population of, let's say 1 million people. And let's say at the very beginning, San Francisco has no population at all. Okay, because LA is too crowded, then a lot of people has moved or migrated from LA to San Francisco. So after, let's say, 10 years, this is before, and this is like 10 years later. So 10 years later, there are 6 million people in LA and then 4 million people in San Francisco. And then let's say starting from that, the population in both cities are kind of, in both counties are kind of balanced, or they are like stable. So every year, there are couples of people who move from LA to San Francisco, but from San Francisco back to LA, the same number of people move back. So let's say from LA to San Francisco, like there is migration of, let's say, 0.1 million people every year. But at the same time, San Francisco people go back to LA, and then the number of the people going back is 0.1 million every year, which means like every year, the population in LA keeps 6 million. The population in San Francisco still keeps 4 million, even though that there are people like going back and forth between them. So when I say something has reached equilibrium, it doesn't mean that there is no communication between them. There are still like people going back and forth between these two cities, but from the macro perspective, the population has not changed. So that's how it applies to the reactants and the products. So let's say, for example, for the Haber process, nitrogen gas, 1 mole of nitrogen gas reacts with 3 moles of the hydrogen gas, and then it produced 2 moles of the ammonia gas, and 2 plus 3H2 to form 2 NH3. So let's say at the very beginning, we have 100 moles of the nitrogen, and then 200 moles of the hydrogen, and then 0 and none of the ammonia. And after a while, they has reached equilibrium. This means, for example, there are like 40 moles of the nitrogen gas and 20 moles of the hydrogen gas, and 120 moles of the ammonia gas. Okay, so at this point, starting from this point, you are not going to observe any of the change in the number of the moles of each of the reactant and all the products. But what's actually happening is the reaction, the forward reaction is still going on, and then the reverse reaction is still going on as well. But every time 1 mole of the nitrogen and 3 moles of the hydrogen is consumed, then 2 moles of the ammonia is also consumed. So that's why you do not actually observe any of the change in the concentration. So you will see 2 different types of the graph in AP Chemistry exam, which represent the equilibrium. One is the concentration versus time. So the concentration of the reactant decreases over time, and then the concentration of the product increase over time. And then at a certain point, the concentration does not change anymore. Okay, then that point is where the equilibrium has reached. And there is another graph which shows the reaction rate versus time. For the reaction rate, eventually at equilibrium, the forward reaction rate is equal to the reverse reaction rate. So these two curves, they will meet at a certain point. So eventually the forward reaction rate and then the reverse reaction rate is the same. So the forward reaction rate will be decreasing. And then the reverse reaction rate is increasing, and eventually they're equal to each other. So these two graphs all like both represent that the system has reached equilibrium. But remember that for the concentration versus time graph, the eventually at equilibrium, the product and reactant does not have to be at the same concentration. Just like LA and San Francisco, the population has reached some kind of balance or they formed equilibrium, it doesn't mean that their population are eventually the same. It just means the population for each of the county is not changing anymore. On the other hand, for the reaction rate versus time graph, the forward reaction rate is always the same as the reverse reaction rate once the equilibrium is reached. That's one of the primary difference between these two graphs. Okay, now let's talk about the equilibrium constant, which is one of the most important concepts when it comes to equilibrium. Okay, so equilibrium constant is represented using the capital letter K. So that is how it is different from the reaction rate constant. Reaction rate constant is a small letter K, and the equilibrium constant is capital letter K, and then it does not have a unit. So for any of the equilibrium reaction, if we ever write it as XA plus YB forms equilibrium between ZC and then WD, then how we actually write the equilibrium constant is K is equal to concentration of the product divided by the concentration of the reactant. And then I raise the concentration of those all the reagent to the power of the coefficient. So concentration of C to the power of Z times concentration of D to the power of W over concentration of A to the power of X over concentration of B to the power of Y. This is how I define the equilibrium constant. And again, it has no unit. And it is always the product over the reactant. Okay, then what does a very large number of K represent? A very large value of K, such as 100, 10, 1,000, etc., it represents that at equilibrium, most of the reagent in the container or in the system are products. It means at equilibrium, products are way, way, way more than the reactants. On the other hand, a very small number of K, such as K cannot be a negative value, so such as 0.1, 0.001, it means that equilibrium, the amount of products are way less than the reactants. And potato, you asked me a question. Is KP also just products over reactants, but with ATM instead of concentration? Yes. So KP, that is just replacing the concentration with the pressure. And then we will go over that later. So for example, let's try to write an equilibrium constant expression for this given chemical equation of 4 moles of ammonium gas reacts with 7 moles of the oxygen gas. And then they form an equilibrium in between 4 moles of the nitrogen dioxide gas and then 6 moles of the water in liquid. Then how I write the equilibrium constant K is product over reactant. So the concentration of NO2 to the power of 4, concentration of, never mind, this one should be in gas, H2O to the power of 6 divided by the concentration of ammonia to the power of 4 divided by the concentration of oxygen gas to the power of 7. This is how I write it. And again, there is no units. Okay, and now let's try to do, how do we do the math with an equilibrium constant? So when you do the math with an equilibrium constant, so let's say the concentration of all of the reactants and the products have been doubled, that what you do is the new equilibrium constant will be the original equilibrium constant squared. So number one, when the all of the reagents have been multiplied by a constant, so for example, this reaction has been changed to 8 moles of the ammonium gas multiplied by 14 moles of the oxygen gas. And then now it forms an equilibrium between 8 moles of the nitrogen dioxide and 12 moles of the water in gas. Okay, so given that the concentration had been doubled, and then do I save it? Yes, I save it. You can come back later and check it on my channel. Then you are going to raise it to the power of that coefficient. So you multiply it by 2, right? Let's say you multiply by 2, then you are going to raise it. So the new K is equal to new equilibrium constant is equal to original equilibrium constant squared. And then the second type of manipulation or calculation with equilibrium constant is now you're going to reverse the reaction. So for example, you reverse it, so now the product becomes the reactants, and then the reactant becomes the product. So 4 moles of nitrogen monoxide reacts with 6 moles of water in gas, and it forms an equilibrium between 4 moles of ammonia gas and 7 moles of oxygen gas. Then now the new equilibrium constant is equal to the reciprocal of the original equilibrium constant. And then the third one is when you add up multiple equations. So for example, when you have the multiple reaction, let's say carbon reacts with oxygen gas to form carbon dioxide. This is equation 1. For this equation 1, the equilibrium constant is K1. There is another equation, carbon monoxide. Carbon monoxide gas reacts with oxygen gas to form carbon dioxide as well. For the second reaction, let's say the equilibrium constant is equal to K2. Then when you add up these two reactions, and you will get a new reaction of carbon reacts with 2 moles of the carbon monoxide with 2 moles of the oxygen gas. And then it forms an equilibrium with 3 moles of the carbon dioxide gas. Then for this reaction, the new equilibrium constant K is equal to the product of the other two reactions. So again, when you multiply the reaction by a constant, you are raising it to the power of that constant. Yeah, I will be live tomorrow too. And if we are reversing the reaction, then the new equilibrium constant is the reciprocal. And if you're adding up multiple reactions, then the new equilibrium constant is the product of those equilibrium constant. And next, okay, the next will be Kp. I think someone just asked me how is Kp different from K. So it's exactly the same. So equilibrium constant, usually we represent it as K, but sometimes we represent it as Kc. So C just means it's concentration. To differentiate it from Kp, which is equilibrium constant represented in terms of the pressure. So we're going to use the ideal gas law, which is PV is equal to nRT. Okay, so the pressure, we have the pressure, we have the volume, we have the number of the moles, and the temperature. So given the temperature is constant, then pressure is equal to nRT over V, or N over V multiplied by RT. And the number of moles divided by the volume is equal to the concentration. So it's basically concentration times RT. So how I can rewrite rewrite the Kp in terms of Kc is, let's say for example, here's an example. So 2 moles of the ammonia gas decompose into nitrogen gas, and then 3 moles of the hydrogen gas. This is the reverse reaction of the Haber process. And if I just write a regular equilibrium constant using the concentration, then Kc is equal to concentration of the nitrogen multiplied by concentration of the hydrogen to the power of 3 divided by the concentration of ammonia squared. Okay, then what about, what if I write it in terms of the pressure? Then Kp, P means the pressure, is equal to, it's exactly the same, product over the reactant. So it's the partial pressure of nitrogen multiplied by the partial pressure of the hydrogen cubed divided by the partial pressure of the ammonia squared. And then now I'm going to replace partial pressure P with the concentration and RT. Then it will be concentration of the nitrogen times RT multiplied by concentration of the hydrogen times RT cubed over concentration of the ammonia times RT squared. So I can rewrite it or simplify it into concentration of the nitrogen times the concentration of the hydrogen cubed divided by the concentration of the ammonia squared multiplied by RT to the power of 1 plus 3 minus 2. So eventually, how I got 1 plus 3 minus 2 is by adding up the coefficients of the products and then subtract the coefficient of the reactants. And remember that we can do this calculation because all of the reactants and products are in gas. So eventually, in summary, Kp is equal to Kc, or just regular equilibrium constant K, multiplied by RT to the power of delta N gas. And delta N gas is equal to number of moles of the gas in the product minus number of moles of the gas in the reactants. Next, I'm going to talk about the reaction quotient. Okay, so reaction quotient. Again, another concept that a lot of people get confused with the equilibrium constant because it looks exactly the same. So reaction quotient, how it looks is, so Q is equal to concentration of the products divided by concentration of the reactants. Then how was it different from the equilibrium constant K? So K is the standard value. So for any of the reaction, there is only one specific K value at every single temperature, but Q can be a lot of different values depending on the initial concentration of the reagent, of the product and the reactant. So Q is totally determined by how much of the reactants and products are in the container right now. It doesn't mean this ideal standard to form an equilibrium. And then the reason we calculate the reaction quotient is to compare with the equilibrium constant at a specific temperature and to determine in which direction the system should shift to reach the equilibrium. So for example, If Q is less than K, then what does that mean? It means compared to the equilibrium phase or compared to the equilibrium state, I have too many of the reactants and too little of the products. Which means if the system would like to reach an equilibrium or achieve an equilibrium, it should shift toward the products. So this is how it looks. This is Q, this is K, which means for Q to reach K, Q has to increase. Q has to increase means the system should shift toward the products. Okay, so the other way around. When Q is greater than K, it means there are way too many products. And then too little of the reactants compared to the equilibrium. So Q has to decrease to reach equilibrium state, which means the system should shift toward the reactants. And next is what's really, really, really important, which is called the Le Chatelier's principle. So Le Chatelier's principle tells us the direction of the shift to reach the equilibrium. So Le Chatelier's principle states that, okay, so now there is an equilibrium, and then let's say you put a press or stress on one side of the balance or one side of the reagent, either on the reactant or the product. So now it's unbalanced, then you will have to shift it toward the other way or the opposite direction to compensate for the change or compensate for the stress. So stress, I mean increase in the concentration or increase in the temperature, or let's say decrease in the volume, increase in the pressure, etc. So all of these. So when there is a stress, the system shifts towards the opposite side to regain equilibrium. Okay, so for example, again, for the Haber process of nitrogen gas reacting with 3 moles of the hydrogen gas, and then the system has reached equilibrium of the 2 moles of the ammonia. Okay, so now let's say they're already at equilibrium. And then I'm gonna adjust the concentration or adjust the condition, and I'm gonna break this. I'm gonna damage the equilibrium. So for example, let's say I'm gonna add more of the nitrogen gas. Then there is an increase in the concentration on the reactant side. So the system should shift toward the opposite direction to compensate for it, which is toward the product side. So it's gonna shift towards the product. So the concentration of the increased amount will decrease a little bit, and then you will have a little bit more of the product, so it kind of balances it out. Or what if I just decrease the amount of the ammonia? Okay, so when you decrease the amount of ammonia, then it's not at equilibrium anymore. And since there is a decrease in the product, the system should shift toward a direction, in a certain direction, to compensate for this loss, which is toward the product again. So it shifts towards the product too. Okay, third, let's say now I am gonna increase the volume, increase the volume of the container by 2 times. So when I double the volume, what happens is the concentration for all of the reagents half. It's because all of them are gas, and then gas molecules, they are free to move, and then they are dispersed within the container, and then they occupy all the volume. So when you double the volume, the concentration of all the reactants and products decrease by 1/2. Okay, then when there is a change or there's a decrease on both sides, what happens is I'm going to take a look at number of moles of the gas for the reactants and the products. So given that all of them have decreased by 1/2, now I'm going to see which side has a bigger decrease, a bigger amount of decrease. So on the reactant side, I have 4 moles of gas. And for the product side, I have 2 moles of gas, which means when the concentration has halved, the change in the reactant side is bigger. The impact or the effect on the reactant side is bigger. So there's a bigger decrease in the reactant side compared to the product side. So I need to compensate for that loss. So the system should shift toward the left side or the reactant side. And now the last one is change in the temperature. Now let's say I am going to increase the temperature. Okay, then if you want to know how the change in the temperature affects the equilibrium position, then you need to know if this reaction is exothermic or endothermic. And for example, for the Haber process, the forward reaction is exothermic. It is a negative value. It doesn't really matter like how big the value is. It can be negative 100 joules per mole. It can be negative 100 kilojoules per mole. Anyway, it is exothermic. That's the most important thing. Well, so how I usually deal with this kind of question is I deal with a change in the enthalpy or the amount of heat absorbed or released as part of the reactant or the product. Since change in the enthalpy is negative, it means it released energy. Okay, so exothermic means it's releasing energy. So energy is produced, which means energy is just like one of my products. So I'm going to put energy on the product side. And when I say increase the temperature, it's just like increasing the concentration of one of the products. So increase in the temperature means the amount of heat is increased. Again, when the concentration of the product has increased, the equilibrium or the system has to shift in the opposite direction to compensate for that increase. So it will shift toward the reactant side. And then how you put the justification in APFRQ portion is you simply just put the words, oh, this is an exothermic reaction and released energy. That's it. And K, equilibrium constant K, depends on the temperature. So at a specific temperature, there is only one value of K. Okay, so now I'm done with the regular type of the equilibrium constant and the equilibrium constant for the gas. Now I'm going to deal with a solubility equilibrium. So solubility equilibrium can be a little bit more confusing because it has more calculation involved. And then on the reactant side and the product side, the phase of or the state of the reactant and products are different. So for the solubility equilibrium, we specifically use KSP, which means solubility product constant. So for example, I'm going to write a solubility equilibrium reaction, such as calcium fluoride in solid dissociates into calcium ion in aqueous, and then 2 moles of the fluoride ions in aqueous. Remember that for the reactant, it's in the solid phase. For the product, they're in the aqueous phase, because for the product, it means they're dissolved in water. So how you actually write the solubility equilibrium constant is KSP is equal to, again, concentration of the product divided by the concentration of the reactant. So it should be concentration of the calcium multiplied by concentration of the fluoride squared divided by the concentration of the calcium fluoride, right? No, it's not wrong. So you're not going to put the reactant, you're not going to put the concentration of the reactant in the denominator. And it is because calcium fluoride is in the form of a solid. And solid or liquid, pure solid, pure liquid, they don't have concentration. Concentration means a certain number of moles of the molecules or atoms are dispersed in a volume. And then when you increase the volume, the concentration should also decrease. But it's not the case for solid or liquid. For solid and liquid, they have the fixed shape and fixed volume. They do not disperse over a volume, and then they do not follow the shape of a container. So calcium fluoride does not have any of the concentration. So for the solubility product constant, it's just the product of the concentration of the products. So this is how I write KSB for this for this equation. Okay, and now let's say the solubility product for calcium fluoride is equal to 3.9 times 10 to the power of negative 11. Okay, then how do you calculate the concentration of the calcium ion and then the concentration of the fluoride ion? Then I will have to write this ICE table. Okay, so initially, again, I don't have to deal with a concentration of the reactant because they're solid. So I just need to write the concentration of the calcium and then the fluoride. Initially, when they're not dissolved in water, their concentration is equal to 0. And later, the change will be positive x and positive 2x. So eventually, at equilibrium, concentration of the calcium is X, concentration of the fluoride is 2X. So I'm going to plug it in this solubility product constant equation. Then 3.9 times 10 to the power of negative 11 is equal to X times 2X squared. So eventually 4X squared is equal to 3.9 times 10 to the power of negative 11. And X is equal to square root of 3.9 times 10 to the power of negative 11 over 4. And this value X is what we call by the molar solubility, or just the solubility. So it is the number of moles of the solid dissolved in the water or the aqueous solution or per 1 liter of the solution. So you can always use this ICE table and then the X to represent it. Would we have to memorize some reactions as exo-endothermic to solve that? Or no, you're not required to memorize any of that. You will always be given. So for example, the molar solubility for the calcium fluoride is X. It's not going to be 2X. And for example, let's say the bismuth sulfide is only slightly soluble in water. So first off, I'm going to start with ICE table again. And then because the coefficient, the mole ratio for these two products are 2 to 3, then the change will be plus 2X and plus 3X. And in equilibrium, I have 2X molar of the bismuth ion and then the 3X mole of the sulfide ion. And KSP solubility product constant for this reaction is the concentration of the bismuth squared multiplied by the concentration of the sulfide cubed. Then it will be, let's say the KSP value for bismuth sulfide is 1 times 10 to the power of negative 15 moles per liter. Then it's represented as 2X squared multiplied by 3X cubed. So eventually that's 4 times 27, 108. X to the power of 5 is equal to 1 times 10 to the power of negative 15. The common ion effect. Will the initial concentration for KSP products be always 0? If it's dissolved in water, then it's always 0. If it's common ion effect, then it's not. But usually for the common ion effect, you will be asked to determine if the solubility increase or decrease, but you are rarely asked to do the actual calculation for the common ion effect. So molar solubility X for the bismuth sulfide is the fifth root of 1 times 10 to the power of negative 15 divided by 108. So now you observe that for every single ionic compound, how you calculate the molar solubility is different. Let's say for the calcium fluoride, you divide the KSP value by 4 and then you take the square root on it. For the bismuth sulfide, you divide a KSP value by 108 and then you take the fifth root of it. So there is no certain rules for finding or calculating the molar solubility based on the KSP. You will always need to take a look at the equation itself, and then you will have to see the coefficient. What is the ratio of the coefficient? Is it 2 to 3, like 1 to 3, or like 3 to 1, or like 3 to 2? So it really depends. And sometimes you are given the KSP for different ionic compounds, and then you are asked to compare their molar solubility. So sometimes you can just directly compare the KSP values, sometimes you can't. So here are a couple of examples. So for example, if this is a binary compound, binary means there are only 2 atoms in this compound, such as silver iodide, copper iodide, and let's say copper sulfate, and you are given their KSP value. So their KSP value is, let's say, 1.5 times 10 to the power of negative 16 for silver iodide, and then 5 times 10 to the power of negative 12 for copper iodide. For, this is calcium sulfate. For calcium sulfate, that is 6.1 times 10 to the power of negative 5. Okay, then can I just directly compare the KSP value? Yes, because for all of them, they dissociate into one cation and one anion. So for example, for silver iodide, when it's dissolved in water, it produces 1 mole of the silver in aqueous and then 1 mole of the iodide in aqueous. So how you write the KSP for it is X squared. So simply the molar solubility X is equal to square root of KSP. So for all of them, they all follow this rule of producing 1 cation and then 1 anion. So their KSP can all be written as X squared. So eventually, if we want to compare the molar solubility or X, then it's just square root of the KSP value. So you can just directly compare KSP and then come to the conclusion that, the ionic compound with the highest KSP has the greatest molar solubility, and then the ionic compound with the smallest KSP has the smallest molar solubility. But for some of the other cases, you cannot. So for example, when you have copper sulfide and the silver sulfide, and then the bismuth sulfide. Okay, so all of these 3 are sulfide. But they all have different number of the cations and anions. So for the copper sulfide, it's going to dissociate into 1 cation and then 1 anion. For the silver sulfide, it's going to be 2 cation and then 1 anion. For the bismuth sulfide, it's 2 cation and then the 3 anion. So which means eventually when you write the KSP value, the molar solubility, if you represent molar solubility as X, then the KSP for copper sulfide is X squared. The KSP for the silver sulfide is 2X squared times X, which is 4X cubed. And then for the bismuth sulfide, it will be 2x squared multiplied by 3x cubed, which is 108x to the power of 5. So you cannot directly compare the KSP value and then come to the conclusion that, the compound with the greatest KSP has the greatest molar solubility. You can't. You will actually have to do all the calculation. So that's it. And then next we can talk about the common ion effect. So for AP chemistry, you don't get tested on the calculation of the common ion effect. You will only be asked on if the solubility increase or decrease. So the common ion effect states that when a solid is dissolved in an aqueous solution with common ion, its solubility is lower or smaller compared to its solubility in water. Okay, then what I mean by the common ion is for any of the compound that dissolve in water, they dissociate into cations and anions, right? So for this aqueous solution, if it contains the cation or the anion, then that's what we call by the common ion. So for example, when you're trying to dissolve silver nitrate, when you're trying to dissolve the silver chloride in an aqueous solution of the silver nitrate, okay, then this is what I call by the common ion effect because they have the silver ion in common. Or when you're trying to dissolve silver, or when you're trying to dissolve the magnesium chromate in a chromic acid, H2CrO4, then they have the common ion as well. So this is what I mean by the common ion. It doesn't matter if that's the cation or the anion. Is it back? Can everyone still see my screen? Oh, okay, great, perfect. Sorry, I think the connection between my iPad and my Mac Mini is not stable for some reason. Okay, so that was the common ion effect. And next, it's the pH and the solubility. And that will be actually the last topic for this unit. And then we can just get into the questions. Okay, so pH and solubility, actually, it's kind of similar to the common ion effect. Okay, so sometimes when you dissolve a compound in an acidic solution or basic solution, the solubility also changes. For the common ion effect, the solubility always decreases. But for the acidic solution or the basic solution, depending on what kind of compound it is, the solubility might increase or decrease. So the general rule is 1. If the product of the dissolved compound reacts with either acid or base, then it means the product is constantly getting removed. So according to Le Chatelier's principle, when the concentration of the product decreases, the equilibrium or the system shifts toward the product to compensate for the loss. The solubility increases. And then the second is, if the product of the compound has ions, so similar to the common ion effect, common to either acid or base, then the solubility decreases. Okay, so for example, magnesium hydroxide. magnesium hydroxide MgOH2. It's slightly soluble in water. When it's dissolved in water, it dissociates into magnesium 2 plus, and then 2 of the hydroxide ions. Okay, so obviously hydroxide ion is considered strong base. So if you ever dissolve magnesium hydroxide in base, then the solubility will decrease. It's just a common ion effect. Okay, but what if you dissolve in an acid? If you dissolve in an acid, then the hydroxide part, it can react with the proton, and it will be just removed. When it reacts with a proton, it means it's just removed from this equilibrium. So when the product gets constantly removed, you need to compensate for it. So the system will shift toward a product. Okay, so the general rule is so let's say the anion, some anion represented in terms of X minus, if it's an effective base. So when I say it's an effective base, it means its conjugate acid HX is a weak acid. Then the salt MX. So M and X, they just represent random cation and anion. Will have an increased solubility in an acid. And then for the X minus, you just need to memorize the following. Hydroxide, and then the sulfide, carbonate, and then dicarbonate, and then the chromate. So these are everything you need to memorize for the anion X minus, which is an effective base. And anything that combines with these ions, these anions to form the salt, such as magnesium hydroxide, such as, let's say, the calcium hydroxide, such as the sodium carbonate, such as magnesium carbonate, such as the bismuth sulfide, all of them, when there is a salt combined with these anions, then they will have an increased solubility in acid. That's it. So that's it for unit. This is unit 7, the equilibrium. And I think now we can go over the questions in the past paper. Is everyone good? Is there any question that you want to ask me? If no, then I will just get into the MCQ question. I will start with only a few MCQ questions, and then we will get into the FRQ questions. So this is the reaction that occurs between hydrogen gas and iodine gas to form hydroiodine gas. All of the reagents and reactants and products, all of them are gas. Hydrogen gas reacts with iodine gas at constant temperature in a sealed rigid container. The gases are allowed to reach equilibrium according to the equation above. Which of the following best describes what will happen to the reaction immediately after additional iodine is added to the system? Okay, so obviously it has already reached the equilibrium, but now it's not equilibrium anymore because additional iodine has been added. So according to Le Chatelier's principle, when the concentration of the iodine or the reactant increases, this means that the system has to shift in the opposite direction to compensate for that change. So compensate for the change, compensate for the increase in the iodine, I will have to decrease its amount a little bit, which means the system should shift toward the products. So what will happen to the reaction immediately? Oh, but it's not asking for the direction. The rates of both the forward and reverse reaction decreased. Oh, okay. Okay, so for the forward reaction, okay, so for the forward reaction, because the equilibrium position will shift more toward the products, so it will actually increase. The rate of the forward reaction becomes greater than the rate of the reverse reaction. So at equilibrium, again, it means the forward reaction rate is equal to the reverse reaction rate. But once you increase the concentration, then the forward reaction gets a little bit bigger. Next is germanium and solid reacts with 2 moles of the chlorine gas, and then it forms an equilibrium in between the germanium tetrachloride and gas. The value of the equilibrium constant for the reaction is 1 times 10 to the power of 10. What is the value of the equilibrium constant for the following reaction? Okay, so everything has been doubled. Okay, now it's originally it was 1 2 2 2 1, and now it's 2 2 4 2 2, and then on top of that it's been reversed. Okay, so if you just simply multiply by 2 and all the concentration has been doubled, then it's going to be 10 to the power of 10 squared, and when you reverse it, you are going to take the reciprocal of that. So it's 10 to the power of 10 squared and then taking reciprocal. So it's 1 over 10 to the power of 20, which is 10 to the power of negative 20. The answer is A. Next, 1 mole of X2 gas reacts with 1 mole of Y2 gas, and it forms an equilibrium between 2 moles of the XY gas. And then equilibrium constant is 3.0, and this is the equilibrium constant calculated using the concentration, not the pressure. A mixture of X2, Y2, and XY is placed in a previously evacuated rigid container and allowed to reach the equilibrium at a constant temperature. Which of the following sets of initial concentration would lead to the formation of more products as the system moves toward equilibrium? Okay, so all of these are the initial concentration of X2, Y2, and XY. Okay, so using the initial concentration, we can calculate the value of the Q. And then by comparing the value of Q to the K, now we can determine which one will shift toward the product to produce more products. Okay, let's say the Q value will be equal to the concentration of the XY squared divided by the concentration of the X2 multiplied by the concentration of the Y2. Now let's try to calculate the Q value for A, B, C, D. For A, that's going to be 0.2 squared divided by 0.4 times 0.4. Okay, and then obviously it is 1/2 times 1/2, which is 0.25, far less than Kc. For B, that is 0.9 squared over 0.3 times 0.3. That is 3 times 3, which is 9, which is greater than the equilibrium constant. For C, that is 0.3 squared over 0.15 times 0.15. That is 2 times 2, which is 4, still greater than Kc. D is 0.2 squared over 0.1 times 0.1. Again, 2 squared, which is equal to 4, still greater than Kc. Okay, so to make sure that the equilibrium position shifts toward a product, then it means right now, or at the initial, for the initial concentration, I have too little of the products, which means Q value has to be less than Kc if you want to shift toward a product. So the only one out of A, B, C, D, A has the Q value smaller than Kc. So A is the right answer. And now let's try to do some of the FRQ questions. A chemist fills a rigid vessel with SO3, sulfur trioxide gas, at a certain temperature until the pressure of the SO3 in the container is 0.83 atm. And the SO3 decompose as the partial pressure of SO3, SO2, and O2 gas in the container are monitored over time. So at the very beginning, the container has only SO3, which is at 0.83 atm, and then for the reactants, they are at 0 atm, so no products at all at the very beginning. And then they gradually, the reactant gradually decompose, and then the products are gradually formed, so they reach equilibrium approximately here. And then abruptly there is some change, which means you has increased the pressure of the SO2. So this is an abrupt change. This is not a gradual change. So most likely you have added a lot of sulfur dioxide in the container. The kinetics and thermal. So yesterday I went over the kinetics, the rate law, the integrate rate law, all the graphs, the zeroth order, first order, second order, the collision model, kinetic molecular theory. I haven't done the thermal yet. So I'm trying to go over all of those important units like kinetics, rate, and then the equilibrium, and then acid base, and then unit 9. So for the unit 9, the first half is actually pretty easy. It's related to thermal. It's just a calculation of Gibbs free energy using entropy and enthalpy. But the later half is the galvanic cell, electrolytic cell. Usually I found my students like struggling with those parts. So I will try to go over unit 5, 7, 8, 9, and then if we have more time, I can go back to the thermal and then other units. Okay, so for this question, answer the following based on the graph. Draw an X on the time axis to show when the system first reached equilibrium. As I said, when the concentration does not change anymore, that's when the system has reached equilibrium. So this is the point. So at this point, all of the reactants and both of the products have reached equilibrium because their concentration are not changing anymore. So this is going to be the point X, where it has reached equilibrium. And 2, describe the change that was made to the system at time T1. So at T1, the concentration of the O2 is not experiencing an abrupt change. Concentration of SO3 is not going through any abrupt change. Both of them are gradually changing, but the concentration of the SO2 is experiencing a big amount of increase, which means the SO2 gas is added to the container. For number 3, after the change was made at time T1, the partial pressure of SO3 increased while the partial pressure of the O2 decreased. Explain this observation. Okay, so according to the Le Chatelier's principle, well, first off, I will try to write down the balanced chemical equation between these 3 reagents. So initially we have SO3 only, so for the forward reaction will be decomposition of the sulfur trioxide. So SO3 in gas decompose into SO2 in gas and then the oxygen gas. Now let's try to balance it. Then it's going to be 2 of the SO3, 2 moles of the SO3 gas decomposed into 2 moles of the SO2 and 1 mole of the oxygen gas. Okay, so now let's say it has already reached equilibrium at T1, but you just out of nowhere added some extra SO2. You added some extra SO2, then it's not at equilibrium anymore. And then according to Le Chatelier's principle, the system has shifted toward a reactant side. So what I'm going to write is, according to Le Chatelier's principle, the system shifts toward reactants when SO2 is added. Because it's shifting toward a reactants, that's why the concentration of the O2 is decreasing. So even though concentration of SO2 is decreasing, but because of that initial increased amount, so eventually it looks like it's an increase. All this before AP. Yes, I know the AP exam is on May the 1st, so I will try to go over as many topics as possible until like April like 30th. Question number E, use this information above to answer the following. Write the expression for the equilibrium constant Kp for the reaction. So for Kp is equal to the partial pressure of the product, which is sulfur dioxide squared, multiplied by partial pressure of the oxygen gas, divided by the partial pressure of the sulfur trioxide squared. And to determine the value of the Kp for the reaction. Now I just need to plug in the equilibrium pressure for all of these three. So what I can do is I can try to plug in these values. So at equilibrium, the partial pressure of the SO3 is 0.5 atm. The equilibrium partial pressure of the sulfur dioxide is approximately 0.33. And then the partial pressure of the oxygen at equilibrium is 0.17. So eventually that is equal to 0.33 squared multiplied by 0.17 divided by 0.50 squared. And then just calculate the value using the calculator. Is there any question for this specific FRQ question? I think this is a typical type of equilibrium questions that you will be tested on AP exam. You're required to read the graph and analyze the graph, and then you have to be able to spot where the equilibrium starts, and then what happens, like what kind of change is it, and then after the change, to regain the expression, to regain the equilibrium, in which direction the system shifts, etc. Okay, if there is no other question, I will just jump into the next one. The following particle level diagram shows a representative sample of the equilibrium mixture represented by the equation given. Use the information from the particle diagram to calculate the partial pressure of carbon monoxide at equilibrium when the total pressure of the equilibrium mixture is 12 atm. Okay, so this is the representation or a diagram at equilibrium, right? Okay, so now based on this diagram, I know the ratio of the different species at equilibrium. And remember that the total pressure for a sample is equal to the sum of the partial pressure of each of the species. So the total pressure is equal to partial pressure of carbon monoxide plus the partial pressure of hydrogen gas plus the partial pressure of the methanol. And then they all add up to 12 atm. And then remember, the partial pressure depends on the mole fraction. So for any of the species, partial pressure for certain gas is equal to its mole fraction multiplied by the total pressure. Okay, so how many moles do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 moles. Out of 10 moles, 1, 2, 3, 4, 5, 6. Okay, so the mole fraction for the carbon monoxide is equal to, the mole fraction for the carbon monoxide is equal to 0.6. And then the mole fraction for mole fraction for hydrogen. These are hydrogen, not carbon monoxide. Mole fraction of the hydrogen gas is 0.6. Mole fraction for the carbon monoxide is equal to 3 out of 10, so 0.3. And mole fraction of the methanol is equal to 0.1, 1 out of 10. So the partial pressure for the carbon monoxide is equal to its mole fraction multiplied by the total pressure. So it's 0.3 multiplied by 12 atmospheric pressure, which is 3.6 atmospheric pressure. E, write this expression for the equilibrium constant Kp for the reaction. Okay, then Kp is equal to Well, I will have to write an chemical equation in between these three species. Then it is going to be carbon monoxide reacts with hydrogen gas, and then it forms an equilibrium between the methanol gas. And now let's try to balance it. Then it will be 1 carbon monoxide to 1 methanol, because both of the molecule has 1 carbon involved, so the ratio of 1 to 1 does match. And then the number of moles of the oxygen also match. Now I only need to match the number of the hydrogen atoms. So for the products, I have 4 hydrogen atoms. So for the reactants, I need to put 2 in front of the hydrogen molecule to match the 4 hydrogen atoms. Then Kp is equal to the partial pressure of the methanol divided by the partial pressure of the carbon monoxide multiplied by partial pressure of the hydrogen gas squared. Any question up until now? Any question? Next. Okay, so CH3OH in gas, it dissociates into carbon monoxide and then 2 moles of the hydrogen. The reaction system represented by the equation is allowed to achieve equilibrium at different temperature. The following table gives the partial pressure of each species and the equilibrium mixture. F. Use the information in the table to calculate the value of the equilibrium constant Kp at the new temperature. Okay, then Kp for this dissociation reaction is equal to partial pressure of the carbon monoxide times partial pressure of the hydrogen squared over partial pressure of the methanol. So I will just plug in all the numbers. So for the last one, so actually I think it's because I cut off the A, B, and C, so I don't really know which one is the reactant or products. So I think more information will be given if you have the complete question. So this is just what I wrote. It might be the other way around. And for question number F, partial pressure of carbon monoxide, that's 4.2. So 4.2 times 8.4 squared over 2.7. That's it. And G, the volume of the container is rapidly doubled. Okay, when the volume is doubled, it means the concentration is everything is diluted to 1/2 of the concentration with no change in the temperature. As no change in the temperature means K has not changed, equilibrium constant is still the same value. As equilibrium is reestablished, thus the number of moles of methanol gas increase, decrease, or remain the same. And justify your answer by comparing the value of the reactant quotient Q with the value of the equilibrium constant Kp. Okay, so for this reaction, how we actually write the Q will be exactly the same as how we write the Kp, right? It will be the concentration of the carbon monoxide times the concentration of the hydrogen squared divided by the concentration of the methanol. So initially, when the temperature has not changed, this value was equal to the value of K. But once the volume has doubled, so when the volume has doubled, it means all the concentration has been halved, which means now the new Q is equal to, so this was the original Q. That was the original value of Q, and now this is a new Q. New Q is equal to, okay, all the concentration has been halved. So it's 1/2 of the concentration of carbon monoxide times 1/2 of the concentration of hydrogen squared divided by 1/2 of the concentration of the methanol. So eventually that is equal to 1/4 times the concentration of carbon monoxide times the hydrogen squared over the methanol. So this is only 1/2 of its original reaction quotient value, or the 1/2 of the equilibrium constant K value, which means the new Q is smaller than the equilibrium constant K, which means we have too little of the product compared to the equilibrium. So as the equilibrium is reestablished, because new Q is less than K, so to regain the equilibrium, it has to shift towards the product to re-establish equilibrium. Which means the number of moles of the methanol is decreased. And dividing by 1/2. Okay, so you have 1/2 here for the numerator, you have 1/2 for the denominator. So these two 1/2 are canceled out, and then you have 1/2 of the hydrogen gas squared. So you are going to do 1/2 squared and then hydrogen gas squared. So eventually you are left with 1/4. Exactly. If the volume is half, the value, not the value, okay. So if the volume is halved, okay, so let's say if the volume is halved, then all the concentration will be doubled, which means the new Q, this is the second situation, the new Q will be 2 times the concentration of carbon monoxide, 2 times the concentration of the hydrogen squared divided by 2 times the concentration of methanol. You will have to put the bracket. So eventually it will be 4 times the initial reaction quotient value, or 4 times the equilibrium constant value. And yes, if the volume is half, the concentration, all the concentrations are doubled. If the volume is doubled, all the concentrations are halved. Okay, that's it. And the next question, okay, so now that is acid and base. So I think we're pretty much done with equilibrium. And is there any other question that you want to ask me regarding equilibrium? Okay, K can only be changed by the temperature. Yes, K only depends on the temperature. And then when the temperature is held constant, the K value is always constant, not changing. Any other questions? If there's no other questions, then I can start the acid and base. I don't think we have time to go over everything in acid and base, but eventually acid base has a lot of topics to go over. So I think it'll be better to start it today, and then we can continue on tomorrow. So for acid and base, first off, I always start with the definition. So for AP chemistry, we use the Bronsted-Lowry model to define the acid and base. Okay, so Bronsted-Lowry, these are the name of the two scientists and then who proposed the definition of acid and base. So they define the acid as a proton donor, and they define the base as the proton acceptor. So by the definition, water can be either acid or base. Water can be both base and acid at the same time. So sometimes it seems like it doesn't make sense, but that's how we define it. And usually it's because we are going to take a look at how different species react with each other, and then in which direction the proton transfer, and then we define the acid and base. So it's not really about the pH value, because we always believe that our pH 7 is neutral, and a pH value of less than 7 means it's acidic. pH value greater than 7 means it's basic. Most of the time that's correct, but water has pH value of 7, it's neutral, but it's still considered acid in some of the reactions. It's considered base in some of the other reactions. And acid, well, what are some examples of acid in everyday life? Like vinegar, lemon, like fruit, a lot of fruit, lime, tomato, grapes, all of them are acids. So usually acid have the sour taste. And then base, they're usually like baking soda, the cleaning products like soap, bleach. So they have bitter taste and slippery feel. But there are a lot of other types of the bases and acids. So I'm going to start with the definition of acid, and then we're going to go back to the base. So first off, usually for the acid, because it's a proton donor, it reacts with water all the time. So acid, for any of the acid, I can just represent it as HA. A is just a random symbol. It can be one atom. It can be like multiple atoms. Okay, so when HA is dissolved in water, then it's in the form of the aqueous, and then it reacts with water, H2O in liquid, and then it forms an equilibrium. So HA, because it's an acid, which means it is a proton donor, so it's going to donate its proton to water. So now the water forms hydronium ion, H3O plus in aqueous, and then the acid forms its conjugate base A minus. So I call the A minus as conjugate base. It doesn't mean that A minus is actually basic. So let's say, for example, hydrochloric acid, the most common type of acid you learn in AP chemistry, the strong acid. When it loses the proton, it becomes the chloride. Chloride is, its pH value is actually 7, and then it does not have any of the proton affinity, which means it is not an effective base, but still we call it the conjugate base of the hydrochloric acid. So conjugate acid and base, they are always a pair. They are just a name for the pair of the acid and base when there is a transfer of the proton between two species. On the other hand, the water, it's a proton acceptor. So now in this reaction, it behaves as base. And then once it has accepted, or once it has received the proton, it becomes the conjugate acid. So for any species, you can always find the pair of the conjugate acid and base. And this is an equilibrium, and this forms an equilibrium. This reaction forms an equilibrium, which means I can write the equilibrium constant for the acid HA. So the equilibrium constant for dissociation of acid, we call this process dissociation or ionization of acid. Then the Ka value for the dissociation of the acid is concentration of the hydronium ion multiplied by the concentration of the conjugate base A minus divided by the concentration of HA. In AP chemistry, you can also write it as the concentration of the protons multiplied by the concentration of the conjugate base A minus divided by the concentration of HA. So technically what's happening is acid HA always react with water. So technically or theoretically, it should be hydronium ion H3O plus, not just proton. But just in AP chemistry, you are actually allowed to you are allowed to replace the hydronium ion with the proton. And now I'm going to talk about the difference between a strong acid and weak acid. So strong acid means that it completely dissociates or fully dissociates in water. And for the weak acid, it only partially dissociates. So for example, when you have 100 molecules, 100 moles of the acid, strong acid H8 dissolved in the solution, then let's say 99% or 98%, so 98 molecules or 99 molecules of the acid dissociates. On the other hand, for the weak acids, only very small fraction. When I say very small, it's really small. Let's say like 1 out of 100 or 1 out of 1,000. Only this many molecules will dissociate. And most of the molecules just remain in the form of HA. Because A minus for the weak acid, the conjugate base A minus have very strong proton affinity. The proton affinity is the tendency or the attraction toward a proton. And then for the weak acid, they have very, very strong proton affinity, very high strong affinity. For the strong acid, they have very, very small proton affinity. They just don't like to be with protons. They prefer to be in their, they prefer to be alone. So this is why the Ka value for the weak acid will be very small. So usually it's even smaller than 0.1. But for the strong acid, the Ka value is very, very big, like much greater than 1. Usually for the strong acid, it will be like 1 or like 10, like 100. There's not so much difference between the Ka value of 1 and 10. It's like 99.9% of the dissociation or 99.99 of the percentage of the dissociation, not so much difference. Most of the molecules dissociate. Okay. And then let's talk about different types of the acids. So we can just classify acid into strong acid and weak acid. Also, depending on the number of the protons it formed, it dissociates into water. We can also categorize them into monoprotic acid and then polyprotic acid. So monoprotic acid, by the name suggests, has only one acidic proton, which means eventually when it's dissolved in the aqueous solution or in water, it produces 1 mole of this acid, produce only 1 mole of the protons. So the examples will be hydrochloric acid, all hydrobromic acid, hydroiodic acid, hydrofluoric acid, etc. When they're dissolved in water, only one proton is formed. For the polyprotic acid, 2 or more acidic protons are formed when they are dissolved in water. So for example, H2SO4 sulfuric acid, such as H2, let's say chromic acid, such as, let's say the phosphoric acid, etc. So what you need to remember is for the polyprotic acid, a lot of people think that, oh, then let's say sulfuric acid can form two protons at one, just in one step. That's not true. For one step, for each of the step, the acid can produce only one proton, which means this is a multi-step process. So what's going to happen is for step one, the sulfuric acid dissociates into one proton and then hydrosulfuric acid. And then for the second step, hydrosulfuric acid dissociates into another proton and then the sulfate ion. As you remove for more protons, the Ka goes down. Yes, exactly. So for hydrochloric acid, because it's one of the strong acid. So even though I put this equilibrium sign, but the Ka value is very, very, very big. So it's actually just the same as single arrow pointing toward the products, because you barely see any of the hydrochloric acid eventually when it forms the equilibrium. On the other hand, for the polyprotic acid, usually when you remove the first proton, it's pretty easy to remove. So this is the H2SO4, the sulfuric acid is a strong acid. So when you remove the first proton, it's very easy to remove it. The reaction or the equilibrium lies far toward the right, far toward the products. But when you are trying to remove the second proton, then it's very difficult to remove it. The Ka value is very small, and then it only partially dissociates. And here are the list of the strong acid you have to memorize. Actually, it's pretty easy to remember them. So hydrochloric acid, hydrobromic acid, hydroiodic acid. So on the periodic table, it's these three halogen combined with the hydrogen. And then it's the polyprotic acid of H2SO4, sulfuric acid, HNO3, the nitric acid, and then H3PO4, the phosphoric acid. And then the last one is HClO4, perchloric acid. And weak acid, there are a bunch of weak acid out there. So let's say CH3COOH, acetic acid, and then let's say propanoic acid, C3H7COOH, butanoic acid, C4H9COOH. There are just a lot of acetic acid. There are way more weak acids than the strong acids. Is there a device to remember the strong acid and weak acid? I don't think so. I just tried to memorize all of them. For the halogen, sorry, I don't think there is any way. Yeah, I've never thought about like what is that? SoCal? Okay, so halogen and then the nitric acid, and then SO means H2SO4 sulfuric acid. Then what is CAL? Perchloric acid? Yeah, I don't think I know any of the tricks when it comes to memorizing. Okay, so I will go back to the topic. So strong acid and weak acids, or the monoprotic acid and then the polyprotic acid. Okay, and then I'm gonna talk about the autonization of water or ionization of water. So this is one of the most important topics in unit 8. So as I stated before, water can be acid. It can also be base, depending on if it's a proton acceptor or a proton donor. So which means water can actually react with itself. And one water molecule react as or behave as an acid. The other water molecule behave as a base. So H2O in liquid reacts with another H2O in liquid. And then there is a proton transfer from one water molecule to the other water molecule. So one of them becomes hydroxide in aqueous, and then the other one becomes the hydronium in aqueous. And we call this process autonization or dissociation of water molecule. And then this reaction forms an equilibrium. And then remember that at 25 Celsius degrees specifically, the K value for this reaction, the equilibrium constant is equal to 1 times 10 to the power of negative 14. And you really have to remember that this is only at the 25 Celsius degree. If the temperature changes, the KW value also changes. Okay, then this is really important because based on this, I can try to draw that ICE table. Okay, so initially, given that before the autonization or dissociation of water, initially the concentration was 0, and then for the change, it will be plus X molar and then the plus X molar because hydroxide and hydronium has the same number of moles. The mole ratio is 1 to 1, which means that equilibrium, both of them has the concentration of X. So Kw is equal to concentration of the hydronium multiplied by the concentration of the hydroxide. Again, I don't have to divide it with the concentration of the water because both of the water molecules are in the liquid phase. Liquid means they only have a fixed volume. So there's no concentration. There wouldn't be concentration for the liquid. So Kw is the product of these two. So 10 to the power of negative 14 is equal to x squared. X is equal to 10 to the power of negative 7. This is especially important because it means at 25 Celsius degree, the concentration of the hydronium and then the concentration of the hydroxide ions are exactly the same, and they are both 1 times 10 to the power of negative 7 mole per liters or molar. This is especially important because we use the pH scale based on the concentration of the hydronium ion. So for the pH scale, it's just a convenient way for people to differentiate the acidity of a substance. So how I calculate the pH is it is negative of log of the concentration of the protons or the concentration of the hydronium. So this means that at 25 Celsius degree, the pH of the water is equal to negative of log of 1 times 10 to the power of negative 7, which is equal to 7. Okay, so this is especially important because 7 is the cutoff line that differentiates between acid and base. So 7 means it's neutral, but there is a really important condition or assumption, which means the temperature has to be 25 Celsius degree. So if the temperature changes, then the cutoff line or the standard for neutral is not equal to 7 anymore. So how we define the pH to be equal to 7 is neutral is based on the concentration of the hydronium in pure water. So it's not like, oh, I just came up with a pH of 7. The Cram Unit 5 is not posted yet. So it's not like, oh, I came up with an idea that pH 7 means oh, it's that this is substance is neutral, and anything above that is basic, anything below that is acidic. And then I decided that accidentally water has pH of 7. No, it's not. So I realized that the water has the concentration of 10 to the power of negative 7. The concentration of the proton in water is 10 to the power of negative 7. And then I just set that value as a cutoff line for acid and base, which means when the temperature changes, the pH value for neutral also changes. So for example, at a higher temperature of about 60 Celsius degree or 55 Celsius degree, the Kw value increases. Kw increases with the temperature. So when temperature increases, the Kw value also increases. So for example, at 60 Celsius degree, I remember K was, I think it was somewhere like 4 times 10 to the power of negative 14. I can't really remember. I think it's either like 4 or 5. Which means at 60 Celsius degree, Kw is still equal to the concentration of the hydronium times the concentration of the hydroxide, which is equal to x squared. So x is equal to square root of Kw, which is 4 times 10 to the power of negative 14, or 2 times 10 to the power of negative 7 mole per liters. So the concentration of the hydronium is higher than the concentration when the water was at 25 Celsius degree. So when you actually calculate the pH value, it will be slightly less than 7, like 6 point something. It is, for example, for this one, because the value of 4 times 10 to the power of negative 14 is not super accurate, but it will be approximately like 6.7, 6.6. So it means at 60 Celsius degree, 6.7 is the pH value for neutral. And then, okay, Kathniel, you said you have watched all the unit cramp videos, and what would be the best way to study? The best way, well, I mean, for now, because you guys are running out of time, there are only like 4 or 3 days left until test, right? So the best way will be just to try to do as many past papers as possible, especially the FAQ questions. And then if you just Google online, there will be some of the posted MCQ questions, and I think those will be really helpful. And then the stoichiometry. So I'm trying to go over the equilibrium and then acid base, and then the thermochemistry, and then the electrochemistry first, because those are the most challenging topics. And after that, I mean, if we have extra time, I think I can go over the live stream with the stoichiometry. KSP, KP, and KC, we already went over them today. So I will post this on my channel, so I'm pretty sure you can like check it out later. Okay, so that was it. Well, we still have a lot of other concepts to go over, but I think we can try to do some of the past paper FAQ questions. Okay, so we can skip the base ones. We can just try to do the acid questions. So for this is obviously the acetic acid, the weak acid, and it reacts to water, and then it dissociates into hydronium, and then the conjugate base. So this is the conjugate base of the acetic acid, and this is the conjugate acid of water. Oh, never mind. This is methanoic acid, not the acetic acid. Acetic acid is CH3COOH. Ionized according to the equation above. Write an expression for the equilibrium constant Ka. Okay, so this will be the easiest question for acid base. So Ka is equal to, again, the concentration of the products over the concentration of the reactants. So it is concentration of the hydronium multiplied by the concentration of the methanoate HCOO minus divided by the concentration of methanoic acid. And B, calculate the pH of the 0.25 molar of HCOOH. Okay, so this is the typical type of question asking you to find a pH value of an acid. And then depending on the strong or weak, the way you calculate it is different. So how you calculate the pH of strong acid is, it's actually pretty simple. So for strong acid, it completely dissociates. So HA reacts with water, H2O in liquid. It fully dissociates into hydronium ions in aqueous, and then the conjugate base A minus. So if I write the ICE table or the ICF table, so F refers to the final because this is basically just like one direction equation. So initially, let's say you are given the concentration of the strong acid. Let's say that is 0.5 molar. Okay, for water, I don't have to consider the concentration. Then at the very beginning, you have 10 to the power of negative 7 molar of the hydronium ions because they are dissolved in water, pure water. And then for the concentration of the A minus, the conjugate base, that is equal to 0. And then the amount of change will be, because it fully dissociates or completely dissociates, so all of that dissociate into hydronium and conjugate base. So it will be negative 0.5. And then for the product side, that is positive 0.5. Another positive 0.5. So finally, for the final, it will be initial plus change. So it will be 0 molar for the strong acid, and it is 0.5 plus 10 to the power of negative 7 molar for the hydronium, and then it is 0.5 molar for the conjugate base. Okay, so as I stated before, how do you calculate pH is totally based on the concentration of the hydronium. That's it. That's the only thing that I care about. And then its concentration is, the concentration of the hydronium ion is equal to 0.5 plus 10 to the power of negative 7 moles per liters. The thing is, 10 to the negative 7 is negligible compared to 0.5 or 0.1, 0.01, even 0.001. So usually when you're given the initial concentration of the strong acid, unless it's like super small value, then usually you can just neglect it, and it's approximately the same as 0.5 molar, which is the initial concentration of the strong acid. So pH value is equal to negative of log of the concentration of the hydronium ion, so which is equal to negative of log of the 0.5 molar. So most of the times, unless the initial concentration of the strong acid is like super small, something like 10 to the power of negative 6 or even smaller, then you can always calculate the pH of strong acid as pH is equal to negative of log of the concentration of that strong acid. Yes, there is a condition unless its initial concentration is super small. If its initial concentration is something like 10 to the power of negative 7, 10 to the power of negative 6, then to be honest, eventually the pH value will be approximately just 7. It will be slightly like less than 7, like 6.9, but eventually it's basically the same as 7 because it means there is very little of the strong acid in a bunch of water. So this is a super diluted acidic solution. So for this super diluted acidic solution, basically it's about the same as pure water. So the pH value is approximately 7. But when it comes to weak acid, it's a different story. So for the weak acid, because it only partially dissociates, so it forms an equilibrium between the weak acid and its conjugate base. Again, I can try to write that ICE table. And let's say the initial concentration of the weak acid is also 0.5 molar. Then the initial concentration of hydronium ion is 10 to the power of negative 7 molar. Initial concentration of the conjugate base is 0. And then the change, because it only partially dissociates, so the change is something I don't know. So I'm going to set it as negative x. Then for the product, it will be plus x. And eventually at equilibrium, it's 0.5 minus x for the weak acid. And then x plus 10 to the power of negative 7 for the hydronium, and then x for the conjugate base. So eventually, Ka is equal to the equilibrium constant is equal to the concentration of the hydronium times the concentration of the conjugate base divided by the concentration of the weak acid at equilibrium. Okay, remember that you will always have to plug in the value for the equilibrium. So these three values. And let's say, for example, for this question, the Ka value is 1.8 times 10 to the power of negative 4. So 1.8 times 10 to the power of negative 4 is equal to x plus 10 to the power of negative 7 times x divided by 0.5 minus x. Okay, for denominator, I have 0.5 minus x. This is not pure math. This is actual like experimental chemistry, which means x has to be a value less than 0.5, right? And then I know that this is weak acid, which means that only partially dissociate. X will be a very small value compared to 0.5. So eventually, anyway, the denominator will be, it's not going to be even smaller than 0.4. Its minimum will be like 0.45 or 0.4 something. Okay, then for the numerator, when you multiply x by another value, which is x plus 10 to the power of negative 7, which is very, very, very small, and then it has to be equal to 1.8 times 10 to the power of negative 4 times approximately 0.5. Okay, so when you multiply by them together, it's just approximately 10 to the power of negative 5 on the left side. On the right side, that's x plus 10 to the power of negative 7 times x. Well, 10 to the power of negative 7 is already small compared to 10 to the power of negative 5. And then you're multiplying x by each other, which means approximately x should be 10 to the power of negative 2 to 10 to the power of negative 3. So when you square it, you will get approximately 10 to the power of negative 5. So x will be some value approximately 10 to the power of negative 2 or 10 to the power of negative 3. This is just a very, very rough estimation. Anyway, this value is very, very big compared to 10 to the power of negative 7, which means x plus 10 to the power of negative 7 is just approximately x. Just like 1.0001 is approximately 1. 0.99999 is just approximately 1. It's negligible. For the denominator, because x is at most 10 to the power of negative 2, it's still small compared to 0.5. So for the denominator, 0.5 minus x is just approximately 0.5. So eventually, I can just write this as an estimation equation of 1.8 times 10 to the power of negative 4 is approximately x times x over 0.5. So x squared over 0.5 is equal to 1.8 times 10 to the power of negative 4. And then x squared is equal to 0.5 times 1.8 times 10 to the power of negative 4. And then you take the square root. So x, which is the concentration of the hydronium in the weak acid, is equal to square root of the initial concentration of the weak acid multiplied by its Ka value, and then taking the square root on that. So by applying this formula, going back to this question, so its Ka value is pretty small, and its initial concentration is 0.25. Okay, so for approximation, the concentration of the hydronium in this amount of weak acid is square root of its initial concentration 0.25 multiplied by its Ka value 1.8 times 10 to the power of negative 4 that is 6.7 times 10 to the power of -3. So pH is negative of log 6.7 times 10 to the -3, which is 2.17 or approximately 2.2. So that's it. That's it for today. The time is up. I will wrap up. So tomorrow, it will be 6 p.m. PST, the Pacific time. And then I will hold 2 more live sessions on the weekends, one on Saturday, one on Sunday. For Saturday and Sunday, I think it will be either morning or the noon. I will post a schedule on my channel, so just check it out, and then you can bring your classmates and or your friends. Yes. So that's it for today, everyone. Thank you for joining, and I will see you guys tomorrow.